Welcome to today's Explainer. Today, we're diving quite literally into the hidden mechanics of fluids. Whether you're tackling the ICSE ninth grade curriculum or you're just a curious mind trying to figure out how the physical world actually works, we're going to take the invisible forces that govern everything around us, from a tiny pebble dropping in a pond all the way up to a massive cargo ship, and make them completely visible and totally understandable. So here's our game plan for today. We'll start with the forces in fluids, figure out what actually causes upthrust, unpack Archimedes' famous principle, look at how to experimentally verify it, and then wrap up with the definitive rules of flotation. But before we get bogged down in the math, I want you to picture something. Why is it that a massive, towering iron ship floats perfectly on the ocean, but if you drop a tiny little iron nail into that exact same water, it sinks straight to the bottom? I mean, they're both iron, right? They're governed by the exact same laws of physics. Keep that paradox in the back of your mind, because by the end of this explainer, you're going to have the exact physics toolkit you need to solve it completely.
Okay, let's kick things off with Section 1, the forces in fluids. So, what exactly is buoyancy? Well, it's basically the property of a liquid to exert an upward force on any body immersed in it. And that specific upward push, we call it upthrust, denoted as F sub B, for buoyant force. The big takeaway here is that the split second an object enters a fluid, whether that's water, oil, or honestly, even a gas like the air around us, it instantly hits this invisible upward push. It's constantly fighting against gravity. Actually, you've probably felt this yourself. Think about taking an empty bottle or an empty can, plugging it up tight, and trying to shove it down into a bucket of water. You can literally feel it fighting back, right? You are physically battling upthrust. The deeper you push that can, the harder you have to press. And the second you let go, bam. The upthrust is way stronger than the actual weight of that empty can, so it just rockets right back up to the surface. Now, because of this constant upward shove, fluids kind of play a trick on us when we try to lift things. This introduces a really cool concept called apparent weight. See, your real weight is what you'd measure in a vacuum, or just standing in the air. But when you're in a fluid, your apparent weight is your real weight minus that upthrust. This is exactly why a heavy bucket of water feels ridiculously easy to pull up while it's still submerged deep inside a well. The water itself is practically helping you lift it. But the absolute second that bucket breaks the surface, whoa, it suddenly feels a whole lot heavier. You just lost your buoyant assist. Moving right along to Section 2, what actually causes this upthrust to happen? Take a look at this block completely underwater. It perfectly shows why upthrust exists in the first place. If you remember your basic physics, pressure in a liquid acts in all directions at once, but crucially, it increases with depth. The deeper you go, the higher the pressure. Notice how the horizontal forces on the left and right sides are at the exact same depth. That means they perfectly cancel each other out. But check out the top and the bottom. Let's break this down step by step to make it crystal clear. First, the bottom of our block is sitting at a greater depth than the top, right? Second, since pressure increases with depth, the upward pressure slamming into the bottom of the block, let's call it P2, is significantly stronger than the downward pressure hitting the top, P1. Third, this mismatch in pressure creates a net upward force. The fluid is simply pushing up harder than it's pushing down. And fourth, if you do the math on that pressure difference, the resulting upthrust, FB, perfectly equals the volume of the submerged object times the density of the liquid times gravity, V times rho times G. Which brings us to a huge milestone in Section 3, Archimedes' Principle revealed. Here is the golden rule, straight from Archimedes himself. When a body is immersed partially or completely in a liquid, it experiences an upthrust, which is equal to the weight of the liquid displaced by it. So what does that actually mean for us? It means the apparent loss in weight you feel when you dunk an object is exactly 100% equal to the weight of the water that the object shoved out of the way. So looking at Archimedes and our V rho G formula, the amount of upthrust you get really only cares about two things. First, the volume of the submerged body. A bigger object shoves more fluid out of the way, generating more upthrust. Second, the density of the fluid itself. This is huge because it completely explains why floating changes depending on what liquid you're in. For example, if you push a piece of cork into water and then try to push an identical piece into something denser, like glycerin, you are going to have to push way harder on the glycerine one. The denser liquid packs a bigger punch, so it gives you a lot more upthrust for the exact same volume. Let's look at the actual proof for this in Section 4, verifying Archimedes' principle. This is where the theory becomes undeniable reality. On one side, we've got a physical balance with a solid cylinder hanging just below a hollow one. When you dunk the solid one in water, the scale tips because it loses apparent weight from the upthrust. But, and this is the cool part, if you pour water into the top hollow cylinder until it's perfectly full, which is a volume exactly equal to the solid one below it, the beam balances right back out. The weight of that water precisely equals the buoyant force. On the other side, we have the classic Eureka can experiment. You lower a solid into a water-filled can with a little spout on it, and as it goes under, the water it displaces spills right out and gets collected in a measuring cylinder.
Let's put some real numbers to this to make it stick. Think about the number 100. Say you weigh a solid in the air, and it's 300 grams force. You drop it completely into the Eureka can, and the scale now says 200 grams force. It just lost exactly 100 grams force of weight. Now you look at a water that spilled out into the cylinder. The volume is exactly 100 cubic centimeters. And since water's density is just 1 gram per cubic centimeter, the weight of that spilled water is exactly 100 grams force. The 100 grams force lost by the solid matches the 100 grams force of water collected perfectly. Archimedes totally nailed it.
All right, final stretch, section 5, the rules of flotation. Consider this your ultimate cheat sheet for fluid mechanics. It all boils down to 3 simple scenarios. First, if the object's weight is greater than the maximum possible upthrust, or, an easier way to look at it, if the object's density is greater than the liquid's density, the net force is pulling it down. It's going to sink. Second, if the weight perfectly equals the maximum upthrust, meaning their densities are exactly the same, it'll float, but it'll be completely submerged, just hovering under the surface. And third, if the object's density is less than the liquid, its weight is less than the max upthrust, so it's going to float partially above the surface, only sinking just enough to displace its own weight in water. And just like that, we can solve our opening mystery. The paradox is solved. Why does the nail sink while the massive ship floats? Well, a solid iron nail has a density way higher than water, so our cheat sheet says it sinks. But an iron ship, it's not a solid block of metal, it is hollow, trapping massive, massive volumes of air inside its hull. Because of this, you have to look at the average density of the whole ship, the iron plus all that trapped air, divided by its total huge volume. That air drops the ship's average density way below the density of water, so it floats. To wrap things up today, I want to leave you with a bit of a brain teaser to test what we've just covered. Think about a submarine. It's a single vessel, right? But it can choose to sink to the ocean floor, it can choose to hover silently underwater, or it can float right up on the surface. If you were the lead engineer, how exactly would you use these rules of average density, weight, and upthrust to make a submarine dive and surface on command? I'll let you chew on that puzzle. Thanks so much for joining me on this explainer today. Keep asking those great questions, and I'll catch you in the next one.